Hi everyone, I'm a journal modeling coach. Start with one number. Among these killed or sent back for major revision as a defense, 72% fail on the data. Not because the writing wasn't pretty, but because the data didn't hold up first. One red rejected stamp comes down, and all those late nights are basically gone. So today I'm going to take apart the 3 data problems an external examiner spots first, one by one. Bottom line, your advisor's red line is really just the line your data has to hold. Here, look at these 3 cards. The 3 most common, most fatal traps. Statistical method, sample and data, and causal inference. Just these 3. In one line, wrong test, thin data, and false causation. We'll take them one card at a time, and I'll push the first one right in front of you. Let's tag this first trap, Exhibit 01. And one more thing, this episode isn't just traps. I promise you 3 things. First, I'll explain all 3 of the most fatal data traps in depth. Second, for each trap, I'll give you a real case with real numbers, so you see exactly how the examiner catches it. Third, at the end, I'll take one full paper and walk you through all 3 gates, start to finish. Oh, and there's a blind review data self-check checklist at the end. Make sure you grab it. Alright, 3 cards on the table. Let's start at gate 1. Trap number 1, the wrong statistical method, with assumptions that were never checked. Why this one first? Because the statistical method is the fastest hard error a committee can catch. Picking a test really comes down to 3 things: what you are trying to do, what type your data is, and how the study was designed. Here's a concrete case. Case A, comparing 3 blood pressure drugs, A, B, and C, 30 people per group, looking at the mean drop in blood pressure. What the author did was run 3 pairwise t-tests across the groups, then report the most significant one. What's wrong? 3 groups crammed into t-tests, Pearson run on an ordinal satisfaction scale, parametric tests forced onto clearly skewed data. All of it. The biggest issue here is multiple comparisons. The more tests you run, the more false positives explode. Do the math. 3 t-tests, each at 0.05, and your cumulative chance of at least one false positive climbs to roughly 14%. So reporting the most significant run is essentially fooling yourself. Now the assumptions: normality, equal variance, independence, 3 prerequisites, and many people check none of them. What do these 3 govern? Whether the distribution fits, whether the group spread is consistent, and whether the observations are independent. Take case A's blood pressure differences. One histogram, and it's clearly right-skewed with a long tail. The normality assumption breaks on the spot. Lay a QQ plot on top, and the points fall right off the diagonal. The parametric assumptions simply don't hold. Line up the 3 group box plots, and the spread is wildly different. Variances are clearly unequal. That fails too. How does the examiner read this? Red pen, straight line. 3 groups should be a single ANOVA, not repeated t-tests. Then the second note, not a single assumption check reported before a parametric test. Method doesn't match the data. Remember this, the examiner doesn't need to recompute anything. What tests you used and whether you checked the assumptions, that's a 30-second call. A red stamp comes down, improper method, conclusion, unreliable. The cost has 3 tiers. Minor means redo the analysis. Medium means a delayed defense. Severe means sent straight back. And the cruelest part, your data was perfectly fine. You lost purely on choosing the wrong test. So how do you fix it? Flip to the fixes. For picking a test, ask yourself 3 questions. 1. Define the goal. Are you comparing, associating, or predicting? Each maps to a completely different family of tests. 2. Check the data type. Continuous, ordinal, count, or proportion. That decides parametric versus non-parametric. 3. Check the design. Independent or paired. How many groups? Any covariates to control for? Here's a quick reference. 3 continuous groups go to ANOVA. Ordinal association goes to Spearman. 2 skewed groups go to Mann-Whitney. And the key line, before any parametric test, report both the normality and the equal variance checks. Back to case A done right, 1 ANOVA plus post hoc pairwise with assumption checks up front. Now it's correct. Remember this line, statistics isn't a button, it's a whole argument. Pick the wrong test, and no matter how pretty the conclusion, it won't stand. That's gate 1, green stamp on it, and we flip to gate 2. Trap number 2, a thin sample and shaky data. What the committee looks at first is whether your sample can carry your conclusion. I'll work this gate in 3 passes: sample size, data source, and descriptive statistics. First, case B. The author sent out 42 questionnaires, then concluded this phenomenon is widespread across the entire industry. And those 42 were all convenience sampling, all from the one company the author happened to work at. Look at this balance. 42 dots on the left pan, a boulder labeled industry-wide conclusion on the right. Of course it tips. When the sample is too small, statistical power is low, and whether the result is positive or negative, you can't trust it. Here's a power curve. At a sample size of 42, power is about 0.3, nowhere near the 0.8 red line. What does power of 0.3 mean? 70% of the effects that genuinely exist, you simply fail to detect. Now data sources. The National Statistics Bureau, government open data, authoritative databases are one tier. Unknown origin, self-reported questionnaires with no documentation, second-hand citations are another. Case B lands squarely in the lower tier. The provenance chain snaps, and the source representativeness questionable stamp comes down. The examiner fires off 3 questions on reflex: representative enough, complete enough, consistent enough. And everyone needs an answer. Taking one company's convenience sample and extrapolating to a whole industry, that step already crosses the line. And there's the data cleaning black box. 58 raw responses trimmed down to 42, but who got dropped and why is all question marks. Descriptive stats, don't fudge them either. This table should carry mean, standard deviation, missing values, attrition, but only the mean is filled in, the other 3 columns blank. The text just says, flatly, the 2 group means was similar, not a word on spread or on missing this. Let alone pasting one raw SPSS output screenshot with 0 interpretation. A screenshot is never analysis. The examiner's red pen sweeps across. Sample size and the scope of your extrapolation are severely mismatched. Second line, no basis given for the sample size calculation, and the descriptive statistics are incomplete. The examiner glances at your N, then at the scope of your conclusion, and knows immediately you can't carry it. An insufficient evidence stamp comes down, and this gate is failed. The cost? Your conclusion gets ruled overgeneralized, the core claim shrinks, and you go back to collect more data and rewrite the scope. And collecting more sample is the most time-expensive thing. It can drag you a whole semester. So the fix? Flip it over. Make the data solid in 3 steps. Step 1. Before sampling, do a sample size estimate. Fix the effect size, the alpha, set power to 0.8, and back out the n you actually need. Step 2. State the source and the sampling method clearly. If an authoritative database is available, don't take the lazy convenience route. Step 3. Report descriptive statistics in full. Mean, standard deviation, missing values, attrition, and the cleaning rules. Leave nothing out. Here's a compliance comparison. Non-standard on the left, standard on the right, ticked line by line, with the conclusion scope honestly put back to within this sample. And one more line. Every figure must be interpreted. Each table has to say clearly what it actually shows. Remember this line. Clean data is what lets a thesis stand. Gate 2 cleared, green stamp, and we head into the most fatal one, Gate 3. Trap number 3, and the most fatal. Mistaking correlation for causation. The moment causes or effects shows up in your conclusion, the examiner locks onto you. Let me stamp it most fatal. This trap carries more weight than the first 2. Look at case C. Advertising spend and sales have a correlation coefficient of 0.9, and the author writes, more advertising causes higher sales. Look at these 2 lines, advertising and sales, climbing in tight lockstep. a big R equals 0.9 in the middle. But that is not causation. Why not? At least 3 kinds of false causation are waiting for you: reverse causality, omitted variables, and measurement error. Reverse causality, you could run the other way. Sales did well first, so the company then had money to spend on ads. Even more common is the omitted variable. A peak season shows up in the middle and pushes both advertising and sales up at once. That third variable drives both sides from behind, and the correlation you see is purely incidental. Go one layer deeper, look at the regression. Sales equals beta times advertising, plus an error term epsilon. The endogeneity crack splits open right here, between advertising and the error term epsilon. Draw a two-way arrow. Put simply, the explanatory variable is correlated with the error term. That's endogeneity. The consequence is hard. The covariance of x and epsilon is non-zero, so beta is biased. The estimate is inconsistent, and the coefficient is simply not trustworthy. Back to case C. All 3 sources of endogeneity hit: an omitted peak season, possible reverse causality, and measurement error in advertising spend itself. Now the robustness table. Change variables, change sample, change method. All 3 columns empty, not one done. Keep in mind, significance under a single specification can vanish the moment you change the spec. The examiner's red pen sweeps across. Causal language, 0 endogeneity handling, 0 robustness, a triple miss. Second line, R equals 0.9 only shows strong correlation. It cannot carry the word causes. The examiner zeroes in on words like causes and affects, a sure catch every time. Red stamp. Conclusion not robust, cannot be accepted. The cost is the heaviest too. The core causal claim is overturned. The whole paper's contribution shrinks. Minor revision at best, redoing the entire empirical work at worst. Causation is a thesis's vital point. Once this gate collapses, half the paper is basically wasted. So how do you fix it? Flip it over. Work from correlation, step by step, to causation. Step 1. Honestly admit its correlation. Change the wording to correlated or associated. Don't reach for causes at the drop of a hat. Step 2. Go find exogenous variation, instrumental variables, difference in differences, fixed effects, regression discontinuity. Pick the one that fits. Here's the 4-quadrant cheat sheet. IV, DID, FE, RDD, each with one line on where it fits best, laid out side by side. Back to case C. You could use competitor advertising or a policy window as an instrument, then use difference in differences to strip out the peak season effect. Step 3. Fill that change 3 robustness table all the way. Change variables, change sample, change method. Take all 3 columns. When the coefficient sign and significance stay stable across several specifications, that's when your conclusion is safe to write down. Remember this. Only once it's robust do you dare write causation. Gate 3 is clear too. Green stamp. And next, I'll walk you through one full case. All 3 cards are done, and each one now carries a green trap avoided stamp. Quick recap. 1. Method and assumptions. 2. Sample and data. 3. Causation and robustness. Now I'll set up a new case file, one complete master's thesis. The claim being, online study time affects final exam scores. Using this one paper, we'll run those 3 gates from start to finish. Gate 1 first. Scores are continuous. Study time was split into 3 groups, yet the author ran pairwise t-tests. Red note. This should be an ANOVA, with normality and equal variance checked first. Once corrected, Gate 1 flips from a cross to a check, green stamp on. Gate 2 next, only 45 in the sample, all from a single school, missing values not reported. Red note. Estimate the sample size first, state the source, report descriptive statistics in full. And the conclusion's scope has to be pulled back from university students in general to this school's sample. Once it's made solid, Gate 2 flips from cross to check 2. Gate 3 is the crucial one. Study time and the scores correlate at 0.6, and the author flatly writes, studying longer causes higher scores. Red note. Careful, self-disciplined people already both study longer and score higher. So the gray ball that pops up in the middle, self-discipline, is the third variable you left out, with arrows pointing to both sides. The fix, add fixed effects. Go find exogenous variation, then fill in the change 3 robustness. Note completed in the margin, green check on. Gate 3 flips from cross to check. Finally, this before and after summary table. The original draft's 3 hard arrows on the left, the 3 non-compliant fixes on the right, the whole column of green checks lighting up at once. This one paper, passing or failing the defense, comes down to exactly these 3 steps. So let me say that line one more time. What the committee catches is never some hard problem, it's the fundamentals. Hold these 3 gates, and passing review is already more than half secured. Alright, 3 cards plus this full case file, case closed, on to the final wrap-up. In the end, it boils down to one line, 3 gates, method, data, causation. At every gate, the examiner is waiting for you to hold it yourself first. I'm a journal modeling coach. If this was useful, drop me a 1 in the comments. I'll send you that blind review data self-check checklist I put together. 13 items in all. Before you submit, just take down the list one by one. It covers test selection, assumptions, sample, source, descriptive statistics, causation, and robustness, the whole set. Hit like, save, and follow while you're at it. Afraid of sleeping up? Then keep it on hand. Follow me, and next time we'll take apart the even deadlier details inside the paper. And finally, back to the opening line. It's not that the writing was bad, it's that the data crumbled first. Hold that data line, and your conclusions are the ones people will actually believe. Alright, that's it for this one. I'm Duking. See you next time. 4 corners close in, and this field guide turns the page.